Let's see if people will trickle in here. I'll watch and see if people are watching us out there. And hello, I want to welcome anybody who is out there currently. We have a lot of people, apparently, according to YouTube, already watching, and for good reason, because we have a phenomenal guest today. We have none other than a very, very esteemed colleague from the Eastern Seaboard, and this is a man who's been an inspiration and a remote mentor to me. Although he doesn't get to have any of the blame for any of the bad things I've done, thanks to his tutelage. But I want to welcome Professor Frank Wilczek, author of A Beautiful Question, and we'll be talking about this book, but also his upcoming book called Fundamentals. How are you today, Frank?
I'm great. Doing very well in this kind of self-imposed quarantine in Concord, Massachusetts.
Yes, you're my second friend from the outskirts of Boston, shall we say? After Shelley Glashow was on last week, and I want to then I'm going to be welcoming your colleague Ray Weiss next week. So I want to encourage people to subscribe to the channel. We're getting a lot of great interviews. We had Sheldon Glashow. I talked to your rival, crosstown rival, Kamran Vafa, 2 weeks ago, and that'll be coming out soon. And then Ray Weiss and Barry Barr. So please stay tuned to the Into the Impossible podcast. But first, we're going to start with this book, A Beautiful Question, which I found quite beautiful. And we were just remarking before we went live about the choice of covers. I always joke, I always judge books by their covers. But in this case, as in many cases, first of all, this book has two covers. It has a beautiful outer dust jacket, which I'm going to dispense with, because how much dust do people really have like flying around their libraries? I've never understood a dust jacket, but I do know that if you don't have a dust jacket, the book is worth a lot less. And here we see a beautiful inner cover depicting constellations. That's my territory. We're going to talk about that. All sorts of fun stuff today with Frank Wilczek, winner of 2004, co-recipient of the 2004 Nobel Prize. And we're going to talk about that event. But first, Frank, I listened to the audiobook. The audiobook has 260 chapters. And I want to point out to you that the New Testament only has 240 chapters. So I don't know if
what is each page a chapter, I guess?
I think each break is each kind of paragraph they turn into an audio chapter, but it makes it easy to get to chapter 200. But I want to ask you,
so you know where you are.
Yeah, right. You didn't design the cover, but you came up with the title. Can you explain the title? Because if I'm not mistaken, it's sort of a double entendre, as they might say.
Yes, The Beautiful Question refers to an actual question, which is, does the world embody beautiful ideas? And that was a question that was constantly in my mind as I planned and wrote the book, and was, I thought, a very fertile theme. And then when it came to making a title, I had a different working title, which I don't remember anymore. But then the question grew on me, and the possibility of having that little play on words, I thought, was too good to pass by. And
a beautiful
and it really is a beautiful question.
Yeah,
it's a beautiful.
So the question of whether or not the universe embodies beautiful ideas, kind of strikes the reader right off the top as provocative, because it's not even clear what a question is, what is beautiful about it, and necessarily why would the universe have some teleological purpose to embody a very human notion, such as the notion of beauty. So the first thing I want to start with is the role of symmetry plays a huge role in this book. And I want to talk about something that you bring up in the book, which is also adorned with quite lovely, gorgeous illustrations that represent aspects of symmetry throughout the universe, so to speak. And I want to ask you a question about the utility of beauty. Can you use, as some suggest, beauty as a guide in science, not only to aesthetically, pleasing endeavors like art, but can you use it as a tool in science?
Yes. Well, first of all, let's go back to the most primitive kind of science, which also addresses this teleological issue, which is that when we construct our models of the world, even as children, as babies, we face insolvable problems. The information that we gather, for instance, on the backs of our retina is not enough to reconstruct a three-dimensional world. We have to fill in a lot of stuff. And so we rely on patterns, we rely on mathematical regularities, usually subconsciously, of course, but we have to learn these things as children. And that's why, to me, it's not a matter of the world being designed to be beautiful, but rather it's useful to us in getting into sync with the world, in understanding it and harmonizing with it and being able to cope with it. That symmetry is a useful guide, and therefore evolution has made us think of it as something that's desirable, that we want to have, that we want to interact with, and that's what we feel as beautiful. So that's the aesthetic version, which I kind of turn on its head. It's not a matter of the world being designed to be beautiful, but us being designed to be in sync with the world and finding it beautiful. Then a miracle happened, I would say, in the 20th century, which is that as we understood the world, the physical world, more deeply, we discovered, well, let me backtrack a little. We got into territory where it was very difficult to do experiments. And when you study gravity, you can look out at planets. When you study electromagnetism, you can do experiments with macroscopic objects, where you working with magnets or rubbing cat's fur and so forth. But when you want to understand the inner workings of atoms, when you want to understand in particular what's going on inside atomic nuclei, which became the big problem of 20th century physics in many ways, it's much, much, much more difficult to do experiments. And so the traditional emphasis of fundamental physics and science, of gathering a lot of data and then from that inferring equations that describe the data in a concise way, was not really available anymore, or lost a lot of its power. Instead, what turned out to be very successful is to guess equations based on some kind of aesthetic principle. And symmetry turns out to be the most important aesthetic principle that's successful here. To guess equations that are highly symmetric and then work out their consequences and see if they can explain phenomena. So it was, instead of going from the phenomena to finding beautiful equations, we guessed beautiful equations and then figured out if they could possibly describe the world.
Yeah,
and it works.
Yeah, it's actually
it works amazingly.
Quite interesting. I'm getting a question from my friend Simon Farmer, who's asking how much of the beauty narrative comes in hindsight. You know, this notion of beauty is only skin deep. It makes me think you're looking into the past, you're looking into the skin, so to speak. But and only later do you find it beautiful. When you were coming up with asymptotic freedom, did you look and say, let me find a very beautiful idea? Was that what happened, or no? It can't be. It must have been that it was retroactively or retrospectively.
No, it was much more down to earth, but that was sort of lurking in the background. I mean, first of all, we were looking at beautiful candidate theory, well, or at least not terribly ugly candidate theories. So we wanted to use quantum field theories, so things which embody general principles of quantum mechanics and relativity. And then within those theories, we wanted ones that had controllable behavior, so you could actually calculate consequences. And then within that, we focused on theories that ultimately certainly in retrospect, but I think even beforehand I would have said this, are the most beautiful quantum field theories. They are quantum field theories that have what's called gauge symmetry. They have enormous amounts of symmetry that random quantum field theories don't have. And so it was very important to investigate the possibility that, maybe those theories do describe the world. If not, we would have learned something. It would have been a disappointment. But it turns out that it's certainly not obvious at first. But if you work with the theories and listen to what they're telling you, you learn that indeed they can be used to describe the world very, very accurately and precisely and concisely and beautifully.
And, in listening to the book and reading the book, I found your writing very evocative and almost poetic in terms. And I'll look up this quote, but there's a famous quote, first of all, from Dirac, that it's more important that your equations be beautiful than that they be correct. But he also said something that to the effect, I'll look up the exact quote, something to the effect that poets, let me see if I can find this, poets, Dirac. Yeah, I think you know the quote that I'm saying. Poetry.
I know it roughly.
Okay.
I'll let you look it up.
Here it is. In science, one tries to tell people in such a way as to be understood by everyone, something that no one ever knew before. But in the case of poetry, it's the exact opposite. And yet you quote everybody in this book, from Walt Whitman to E.E. Cummings. You have a phenomenal ability to kind of go into the esoteric of poetics. So tell me, do you find it as distasteful as your fellow laureate, Mr. Dr. Paul Dirac?
No. I kind of like poetry. It's mind expanding. The sentiment that he expressed, and maybe it's a related but different quotation, is that in poetry, in physics, you try to express complicated ideas in the simplest possible way. Mm-hmm. In poetry, it's just the opposite.
Yes.
And of course, there's something to be said about describing things in different ways. This can be very fruitful. The most concise description may not exhaust the possibilities for relating to or understanding or interacting with some system, especially as the systems go from being atoms to human beings or flowers in between, right? There are different levels of description, and poetry can add, mm-hmm. for sure. Yeah.
And of course, Feynman said something to the effect that, why is it worse for him to describe Jupiter as a giant ball of methane than a poet to describe it as if it was a poet using poetic license as if it was a man.
Right.
And I kind of
my point is that it's not either or. It can be both. And this is actually very, very closely related to a deep philosophical principle, which is also a deep principle of physics, which is complementarity, which is that you can have different descriptions of the same object or the same phenomenon that each are valid in their own terms and each answer important questions, but they answer different questions. And if you try to use one description to address inappropriate questions, it can run out of steam or actually be wrong. Originally, this was applied to position versus momentum in quantum mechanics, where it's a theorem. But I think it's a much, much more general phenomenon. So, for instance, it applies to this question of free will versus determinism. For some purposes, it's good to think that we have free will, but for other purposes, it's better and more realistic to think that we're largely determined.
Mm-hmm. And oftentimes we find complementary approaches. You go through a good deal of the beginning of the book, talking about Pythagoras, and it's good to see him getting some citations. His H index was suffering lately, but it's good to have Wilczek quoting his work. But you talk about the unification, the complementarity, the unification of physical, tangible mass being unified or coupled to the notion of pitch or harmony and frequency. You want to talk a little bit more about that, and then we'll get in. So we went from poetics, which is a form of art. Now we're going to talk about sound, and then we're going to get into light, and then later we'll get into some sort of ideas that I have come across that I would love to run by you in terms of time translation, asymmetry, and so forth, which you don't get into this, so much in this book, but you do in your next book, Fundamentals. We'll be talking about that.
Right.
Just a reminder, we're talking to Frank Wilczek, Professor Frank Wilczek, winner, co-recipient of the 2004 Nobel Prize in Physics. I ask you to leave a comment and subscribe. And Frank, as you know, it's really bad nowadays at home. We're getting a lot of carpal tunnel syndrome. So stretch your thumb and click on the subscribe button and leave a like for the Into the Impossible podcast. That's the only way I get people like Frank to come on the show. Talk to me about the unification of things like mass and frequency. Those are two very disparate concepts that I don't think, even as a physicist, I'd really grasp that their significance of their interrelationship.
Okay, so we have to do that in two steps. Yes. So first, there's a relationship between energy and frequency. This is an aspect of particle wave duality, if you like, that in quantum mechanics, we learn that there are complementary descriptions of physical objects, one of which is appropriate to asking questions about position, and the other of which is appropriate to answering questions about momentum, or roughly speaking, velocity. And similarly, we have descriptions in which we talk about the energy of things, or we talk about the frequency of things. And to be precise, in the case of photons, there's a relationship between those two concepts, which is that the energy of a photon is related to its color, its frequency, by a very simple mathematical formula, E equals h nu, which was discovered really before modern quantum mechanics by Planck and Einstein. So energy is linearly related to frequency in quantum mechanics, and that's a really extraordinary thing, because you think of frequency as the sound of a note or the look of a color, whereas energy seems to be something quite different, and yet this profound relationship exists. So that's one relationship. So E equals h nu, that's one equation to keep in mind. The other equation to keep in mind is E equals mc squared, that energy can also be related to the mass. The energy of a particle when it's at rest is proportional to its mass. And then if you put those two together, you learn that mass is related to frequency. So we have this relationship between something you think of as very kind of earthy, ponderous, and something you think of as dynamic and moving and somehow associated with radio waves or music or
quantized.
But they're mathematically related. Mm-hmm. Yeah, and then let me introduce yet a third idea, because this is a great theme, which is that in quantum chromodynamics, in our theory of the strong interaction, we really reverse E equals mc squared into m equals E divided by c squared, where we learn that most of the mass of protons, almost all of it, and neutrons and atomic nuclei in general, and therefore almost all of our mass as human beings, is actually constructed from energy. The building blocks out of which we build these things are massless particles, gluons, and very, very nearly massless particles, quarks. But they're moving around inside protons. They're very dynamical, so they carry a lot of energy. And if you add up all that energy and divide by c squared, you get the mass of the proton. So we have this fantastic sort of movement back and forth between energy and mass and frequency, and beautiful equations that require particles to be mass equals zero, and yet constructing a world where things do have mass. So to me, that's one of the very high points of 20th century physics, well, of human civilization, really, to understand that origin of our very tangible mass in terms of really ideally beautiful mathematical concepts.
So in terms of beauty and sort of mathematics becoming embodied, you quote a lot as we move from from Newton and Pythagoras, a little bit more modern, into discussing now Hertz and Maxwell. You talk about how Hertz, the German physicist who proved experimentally the existence of new electromagnetic waves that Maxwell had predicted, what we now call radio waves, he said of Maxwell's equations, one cannot escape the feeling that these mathematical formulae have an independent existence and an intelligence of their own, that they are wiser than we are, even their discoverers, that we get more out of them than was originally put into them. You kind of, built on this with David Gross back in the 70s. And of course, Frank Yang, who I'm hoping to get Frank on the podcast. The other Frank, Frank Yang, CN Yang on the podcast. He's getting up there in years, but I'm hoping to get him on the podcast. That would be a real treat. The Yang-Mills equations.
That would be remarkable.
Yeah, and I'll let you know. Maybe you can do a guest spot when he comes on with Jim Simons, who's of course my friend and benefactor behind my experiment. But at any rate, what you guys did is sort of, you and Yang and Mills built upon Maxwell's equations. And actually, now we think about, QCD as sort of having this power. And I wonder, did you unleash too much power? As Hertz said, was it wiser than the discoverers, than you and David yeah.
Much wiser than we, much wiser than us. we certainly didn't anticipate all the consequences that have flowed from our basic discoveries. I mean, I did realize very early that within a few weeks that this could be the theory of the strong interaction, and we could look forward to actually experimentally checking it, and so that I already thought, well, we'll get a Nobel Prize for sure out of that if it works, but there was much more that we didn't understand and much more that we didn't anticipate. So we didn't understand for sure a crucial property of the theory with quarks and gluons, which is how quarks and gluons are inevitably confined into more complex objects. So whereas with atoms, you can separate them into nuclei and electrons, with the strong interaction analogs, you can't separate them into their constituent quarks and gluons that the equations tell you were there. And that was a very new and troubling concept to the physics world, that you could have particles within your equations that you could never observe. And we thought that would be possible because the theory is complicated and it's full of massless particles, which have ways of reorganizing themselves and very singular behavior as you try to pull them apart. But we certainly couldn't prove it or calculate it. And that was kind of a leap of faith. We calculated things that we could calculate, but we left a lot of things open. It would be wrong to say that we left some details open. We calculated a few details and left almost everything open. And then the applications to the experiments that we were explaining were kind of limited, and at that time very imprecise and needed a lot of interpretation. I certainly didn't anticipate that at higher energies, the underlying structure of the theory would become so much clearer and easier to understand. Then in really high energy events, the quarks and the gluons that are emitted at very, very high energies kind of leave trails behind, like jet planes would leave a path. And that makes them easy to see. And so, although you can't see the quarks and gluons themselves, you can see those so-called jets and check the theory in very great detail. You can also use the basic theory to understand the structure of the events. And that's become the dominant method of very high energy accelerator physics. You have to understand those things, which are sort of a trillion times more common. If you're going to find the Higgs particle, for instance, you have to understand the so-called backgrounds very well. In the early days, it was very exciting, and we talked about checking QCD and seeing if this was the right theory. Nowadays, it's called calculating backgrounds, but it's the same. It's the same activity. In fact, it's much more rigorous now, but it sounds much less glamorous.
Yeah.
And also, I sort of anticipated, but I didn't anticipate how dramatic the consequences would be, that we could start to study the very early universe in a rational way, because we had now the dominant interactions under control, and they got simple at high energies as opposed to complicated. So it's actually in many ways easier to calculate the properties of matter in very close to the Big Bang than it is, say, in the center of the Earth. We have much more powerful approximations that apply in the former case, but not the latter. So opening up the early universe to view was something I didn't anticipate right at first, but within a few months, I realized that would be possible and started working on
it. So I want to get into to the aspects of testing these beautiful ideas. But before I do, since you brought it up, I wasn't going to go here, but you brought up this little medallion. You mentioned the Nobel Prize. So now it's fair game. Now I could mention it. And my feelings on the Nobel Prize are well known, as you can tell by the room I'm in.
Well, I could see it's in your background. You must be aware.
As Oscar Wilde said, a boy must hustle his own books. I'm not going to mention my polemic, but I do want to say, I've always been curious, since you are a legendary person. I mean, you're extremely modest. You're basically free of ego, as I can tell. I mean, I've talked to Betsy on Twitter. But anyway, but I want to mention,
if you say so.
I just want to know, from a human perspective, you discovered these, asymptotic freedom with David, your advisor, 1973. And it took, 30 years, almost, 31 years before you were rewarded with the Nobel Prize that everybody on God's green earth knew you guys deserved. What was that period like? And it wasn't like you were waiting for verification. I mean, all these things were verified almost immediately after the jets, and they became a tool, as you just mentioned, not only for investigating the substructure of hadrons, but for the early universe as well. On a personal level, Frank, how did it feel, this waiting 31 years for the inevitable to occur?
Well, it was annoying, and if you think about the half-life, okay, so the clock starts ticking, and I'm 21 years old or something, and then if it doesn't happen for 30 years, and then it doesn't happen for another 30 years, it's getting a little iffy, right? So that was one way of thinking about it, but on the other hand, I realized, I think that now I appreciate that living through it was difficult, frankly, really was difficult. But in retrospect, I learned some things, and I also realized some things that make it that would have eased the pain, so to speak, which is, first of all, that the Nobel Committee is very, very conservative. They're very protective of the reputation of Alfred Nobel and the prize. So they really want things that have somehow, or at least in almost all cases historically, have wanted developments that have empirical verification and that won't turn out to be wrong. And that would be embarrassing. And in our case,
no comment.
Our theory makes in our case, since the theory made such precise predictions, that meant it could be wrong. It could be proved quantitatively wrong or missing something major. I think most theorists who are competent to judge, certainly by the late 70s, early 80s or so, had a lot of faith in the theory. But experiments were coming up with LEP, the big electron positron collider, which would do much more precise tests. And so that you could wait on that, and they did. And then the other aspect is that our work built on work of others in a major way. So on the experimental work of Friedman, Kendall, and Taylor, especially at SLAC, where they discovered the so-called scaling phenomena, that was really the phenomenon that we aimed at in our initial investigations. That was the kind of experimental fact about quarks that we wanted to understand. So until they got the Nobel Prize, it would have been very anomalous for us to get a Nobel Prize. And then on the theoretical side, we were also building on especially the work of it Hooft and Veltman, who sort of showed how you could do some powerful kinds of calculations in the kinds of tricky theories that we wound up using. And so I didn't think we would, so they had to come first also. So there's an ordering. Mm-hmm. So the reason it took so long for us is that it took so long for them, I think.
Yeah. So let's get back to the impersonal now. You talk in the book a lot about unification, about complementarity. And I get a lot of emails, as I'm sure you do. You probably get these on steroids. Although I had Adam Rees on the show over the summer, and I said, I get all these emails, basically once a day, and it says, Professor Keating, I've got a new theory of everything. I can't do the math, but if you help me do the math, I'll share my Nobel Prize with you. And I say, and Adam leaned in and he said, "How do you think I got my Nobel Prize?" But it's always, people are always saying, Einstein was wrong. And I wonder, I talked to Barry Barish, and that interview will air next week or so, I believe. So please, everybody, subscribe to the Into the Impossible podcast if you want to hear more great interviews. But returning to the Nobel Prize for just one last moment, Barry told me that he always suffered from imposter syndrome his whole life, and none more so than when he went to collect his Nobel check and sign this logbook, which must have your name in it. And he saw not only your name, but he saw this guy's name, Albert Einstein. And it gave him tremendous imposter syndrome. Do you ever feel imposter syndrome, especially or the nagging period of 3 decades between discovery and the award?
No.
Okay.
I really don't. And there's a reason for it, which is very concrete. I got over imposter syndrome when I went to college, I guess, or maybe even before, because I was in the New York City school system. And at that time we had a lot of tests. We had a lot of grading and tracking, they call it. And I got a lot of encouragement from that process. So, I knew I had done very, very well on objective measures of intelligence and so forth. So I didn't feel like, I'd never felt like an imposter. And then, even when I went to the University of Chicago, things were very easy for me. I wish I had worked harder. In many ways, I wish things hadn't come so easily. When I got to Princeton, things didn't start off by coming so easily, and it was kind of a rough transition. But no, I fortunately, a consequence of early success is that you get confidence. And I think that's extremely important to a research scientist. Confidence is pure gold. Yeah. I mean, because it allows you to think think in different ways, to not worry about what other people think so much, and to think that you could, to take on big problems because you think that you have a chance of doing better than other people have done on them.
Yeah. Conversely, do you feel like afterwards, after winning it, that you had some superpower? I mean, it's rumored that your fellow laureate, T.S. Eliot, said something to the effect that the Nobel Prize is a ticket to one's own funeral, for no one has done anything after he won it. But you're a counter example to that. But do you feel the converse effect, the anti-imposter syndrome takes over once you actually do receive the Nobel Prize? In terms of confidence?
Well, since I did have so long to think about it, I did think about the afterlife, so to speak. And I looked around, and there are many people I admire that had won Nobel Prizes, and I looked at their lives after the Nobel Prize, and some had done better than others. Mm-hmm. And to me, the success stories, like Feynman, like Yang, like T.D. Lee, are people who kind of took it in stride and went on writing papers. Whereas there are some other people I won't name that kind of got intimidated by the prize. They thought that nothing they could do afterward would live up to what they had done before or to the prestige of the prize. And I wanted to be like the first group, not the second group. So sort of I planned right away that after getting the prize, I would write some papers that might be mediocre just to have done it, just to break the ice. And that's what I did. And I kept working. And well, I've been fortunate in that a lot of the ideas that I had early in my career have had a very big afterlife, like anyons and axions. And so, I can build on that. Mm-hmm. They're still at the frontiers of research. But also, fortunately, my style has always been to do something, try to make a basic contribution, and then to move on and do something else. I'm not someone who sticks in the same place and digs deeper and deeper. I move from one thing to another. Mm-hmm. And with that style, you're often going to fail. So I got used to failure also. and so I wasn't afraid of failure either before or after the Nobel Prize. So I didn't get intimidated by it. No.
So I want to talk now about some of the work you've done since then, including your recent work on unification of forces. First, I want to take a break to just recognize our guest. We're talking to Professor Frank Wilczek about his book, A Beautiful Question, which is upside down, it's too bad it's not perfectly symmetrical, or else I would have been able to pull that off. But this is a beautiful book, and I learned a tremendous amount. I got great insight, as you will, into what it's like to be a physicist and to think about the existential questions, but to do so with an artist's eye and maybe a musician's ear and whatever other a sculptor's fingers or whatever.
Well, I think very important is a historian's appreciation of human endeavor. I really enjoy learning about the history of ideas.
Yeah, and you go way back, as we said, to Pythagoras, to Aristarchus, boosting their H indices as we go.
To think about how these great minds wrestled with difficult problems and the paths that they went down that we now know were mistaken, but why did they seem plausible? How did they explore them? I've learned a lot and been very inspired by studying the history of ideas.
Yeah, and I think that comes through in this book. And you talk a lot about Isaac Newton, not only for his role, along with Maxwell himself, James Clerk Maxwell, who, if I'm not mistaken, is your role model as a physicist, is your kind of favorite physicist in history, as you are to probably millions of people around the world, Frank. But I want to say about Newton, what really is amazing about Newton, and certainly, later people like Faraday, etc., was that they had this deep love of solving puzzles, and it's reputed that they would think about these things really without ceasing. Einstein as well, this toy that Anthony Z talks about as kind of his most magical thing was getting a compass from his dad. I wanted to talk about experiment, because I'm an experimentalist, which I always joke, there's a joke. What do you call someone who hangs out with musicians? You call him a drummer. What do you call someone who hangs out with physicists? You call him an experimentalist. I can say that. You can't say that. But I get emails every day about, Professor Keating, as I said, Einstein was wrong. Not only is going to the Nobel Prize, but going to this notion that that we somehow want to outdo Einstein, that we want to do what Einstein didn't do, maybe as a favor to the old man, or maybe as to vindicate him. He certainly didn't do as much that was really held in high esteem after he did win the Nobel Prize. But getting to his dream of a so-called theory of everything, I've been talking to Roger Penrose, I talked to Lenny Susskind, I talked to Kamran Vafa and many others. Luckily, I'm very blessed to have them as members. Oh, and reminder out there, exercise your fingers. Don't get carpal tunnel syndrome. Press the subscribe button, the like button. We can get more time with Frank Wilczek. He is such a gracious person. He has not only agreed to come on today, but to time translate and use that symmetry to next month in January. He'll be back on to talk about his new book, Fundamentals. That's a phenomenal book as well. Anyway, getting back to Einstein and unification of forces. There is the common thread that runs through almost all these emails and topics that I've been talking about with people like Penrose, et cetera. This notion that we need a theory of everything because we don't understand how to unify gravity with quantum mechanics. I want to just push back on that notion. As an experimentalist, I said this to Roger to his face. I'm not speaking out of school. I said, no one's ever going to go into a singularity. I mean, Lenny talks about that in his book. You can't visualize a singularity. And people like Roger in his book, Cycles of Time, which we talked about last month, right after he won the Nobel, or was announced to be the Nobel Prize co-recipient. We talked about his model for conformal cyclic cosmology, which does away with the initial singularity, at which point people were using as motivation for a theory of quantum gravity. I'm going to talk to you later about your paper with Lawrence Krauss about inflation and unification of forces. But first, why do we need a theory of quantum gravity when we can't know for sure if there was an initial singularity? And two, we can't access what occurs at the core of a black hole. And three, we have no example. We have no example in nature of an infinite quantity smoothly transitioning to a finite quantity. So why do we need to unify gravity with quantum mechanics at all?
Okay, well, at a practical level, we probably don't. I'm sure as a practicing astrophysicist, that in astrophysics, people deal with situations where gravity and quantum mechanics are both important at the same time. Every day, that's the world, and it's as common as dust that you have gravity and quantum mechanics.
Dust is a four-letter word on the show, Frank. Dust is a four-letter word. I would have had one of these if this
have gravity.
This got in the way.
Quantum mechanics working in harmony to describe the natural world in great detail with great accuracy, but. When you push things really, really hard, when you try to calculate tiny corrections due to quantum fluctuations of gravity, you find that our existing theoretical apparatus doesn't give any sensible answer. And you would like to understand situations where things do get very extreme, like at the center of black holes, but maybe like the very, very early universe, so that's a kind of quasi-practical application. And then there's finally the simplest reason that you want to do it is that gravity is there and quantum mechanics is there, and you want to have a consistent theory that includes both. So it may or may not be important for any practical or even theoretical problem, but it's a challenge. It's an intellectual challenge, if you like, and it might have unexpected consequences. In fact, I think a quasi-unexpected but potentially important consequence is that we have a model called inflation that seems to explain a lot about cosmology, as you know. But its foundation in theory is very, very shaky, I would say, and the existing models of inflation are sort of a counterexample to beauty in physics, I would say. They're really super ugly and don't really fit experiment very cleanly. And so there's something missing in our understanding of early universe cosmology, and it's quite possible in my mind that understanding quantum gravity better will address that cluster of real questions that are connected to actual observations. Okay, I think that answers your question. If I may,
yes, that.
If not, we can.
Yeah, actually, let's go to what kind of is an allied question, a concomitant question. But before we do that, we just received a chat from a very munificent and generous listener who is paying us $10. Not you, Frank. I'm sorry, but it also go to my $5.29 college savings plan for my kids. And Pete is asking the following question. He is asking, wouldn't a more complete understanding of gravity potentially enable us to do more to manipulate gravity? No, that's provocative.
Well, it's conceivable, of course. Until we have the understanding, we don't know what we can do with it. But it seems far-fetched to me. Let me tell you why in very concrete terms. So consider the LIGO experiment, which in recent years succeeded in detecting gravitational waves. They had to work very, very hard to be able to observe any effect. They had to develop new methods of keeping things from shaking. They had to make innovations in laser technology. They had to build things on a grand scale. The apparatus are 4 miles long, and you have to have several of them all around the world. And so it's a very, very challenging enterprise. And you're looking for effects where the distortions produced in space-time by gravitational waves are smaller than the radius of a nucleus by a considerable factor. So it's
not
so that's manipulating gravity or manipulating space-time. And what did it take to do that tiny effect? It takes 2 gigantic black holes colliding, and just in the last moments of the most violent collision, they produce this tiny, tiny signal. So the point is simply that gravity is a very, very weak force, fundamentally. And so I think the prospects of doing engineering with it at a quantum by better understanding of the quantum mechanics of gravity is very, very far-fetched. Now, time may prove me wrong, but I doubt it.
Well, they laughed at John Newhousen some, right? Nobody knows who that is because he was wrong. But I just want to give a little tease. I can't resist it. So people in the 1700s looked at lightning and they would have said, "Oh, we can never, approach the fearsome power of the electron," or whatever they would have called it. But then allegedly, none other than my hero, Michael Faraday, said when asked by William Gladstone, the British Prime Minister British Minister of Finance back then, about the practical value of electricity, Faraday said, "One day, sir, you may tax it." That's right. Yeah. So
and
maybe we'll tax gravity.
No, that's
or
that's a warning.
Yes.
That's a warning. But on the other hand, now we understand things much better and much more completely. So
yes.
The idea that we're missing something enormous that could be used in engineering is a lot more challenging. And what's the other thing I was going to say? Never mind. Yeah. That's enough.
Yeah. So I want to get to this, and I have a lot of comments from people in the audience. Sometimes I do a poll and I say, leave a comment if you have a theory of everything, and then give a thumbs up if you've heard about a theory of everything recently. So let's do that. But I want to talk about your paper. This is from 2014. Soon after my team and I released the Bicep 2 results, you and Lawrence Krauss wrote a paper from B modes to quantum gravity and unification of forces. The reason I want to go here is that I feel it's very important for scientists, if they have a theory of everything, to pursue all existing avenues of data. And you just gave an example
Right.
which was meant to be kind of illustrative of how hard it is to do experiments in gravity. But what if I told you,
Yes.
most of the time I get these theories of everything, someone like Garrett Lisi or my friend Eric Weinstein, who may join us at the end of the show. The question of, well, I want to test this theory, but it relies on such high energy phenomena that we will need a bigger particle accelerator. And I always say, like, imagine if you wanted to test gravity and you said, I want a bigger particle accelerator. I'd say, well, how about this? I have a neutron star collider. Will that do? I'll take two neutron stars at 99.9% the speed of light. I'll crash them together. Would that do? In other words, why aren't people as willing as you were to look at the low energy limits of different phenomena? As you said, asymptotic freedom was sort of confirmed not through direct observation of quarks, but through the jet processes. That was very, very hard to do, but it wasn't as hard as finding the Higgs, right?
No, well, it made finding the Higgs conceivable, actually. But well, that's an example where I think we would have been justified in saying that we need higher energy accelerators to really test the theory, and that worked. In the case of quantum gravity, though, we can estimate what the required energies are, and they're just not going to be available anytime soon, and maybe never. You would need accelerators the size of the solar system and an energy budget which is way beyond human energy consumption. So don't hold your breath on that one. Now, but on the other hand, if you have a bright idea, you might be able to see consequences of quantum gravity at low energies. And this work I did with Lawrence was an example of that, where, well, it's using the early universe as an accelerator.
Yeah.
So you could find relics left over from the early universe. You get to also look at signals from colliding black holes, as I mentioned, or black holes and neutron stars. So there is data out there. And in general, I have very little sympathy for theoretical physicists who say, "Oh, my theory is great, but you can't test it." Mm-hmm. That's a failure. That's not an excuse. That's just a failure. And okay, in a more constructive vein, I've been thinking recently about the quantum nature of gravitational radiation. It has been treated as a classical field that rattles around the things in LIGO in a certain way based on classical mechanics, basically. But in reality, the black holes produce a quantum field. Everything is quantum, and the black holes create a quantum field of radiation. And they're very different, I'm discovering. And I hope there'll be observable consequences from that won't require gigantic new accelerators other than the black holes.
Mm-hmm. Yeah, we experimentalists are a greedy bunch. We want future circular colliders. We want international linear colliders. We want LIGOs in space. But I wanted, to get back to that paper that you wrote after BICEP 2 results came out. As you just mentioned, the phenomena of gravitational waves leaving a B-mode imprint in the polarization of the microwave background is based on classical perturbations, not quantum mechanics. So what would be a definitive early universe test of the quantum nature of gravity? That is the graviton, so-called graviton.
Well, in that paper, we argued that observation of gravitational waves from the early universe that had basically a thermal character was a strong indication of the quantum nature of gravity, in the same way that observations about the black body radiation led Planck and Einstein to propose quantum mechanics in the first place. So there's an H bar that appears in the equations, and that's a pretty sure sign of quantum mechanics. But I'm still hopeful that there would be more encompassing implications, maybe new models for how to produce the phenomena that we currently ascribe to inflation, maybe some heterodox version of inflation that's driven by gravity itself rather than some ad hoc inflaton field made. I guess, what was the question again?
Yeah, just
got carried away.
What is a fundamental? When I think of quantum mechanics, I think of spooky action at a distance. Number one, I think about electron double slit experiments. What is the analogous? Because I agree with you. I don't think we could do an experiment on gravitons the way we do with photons. But what conceivable test of early universe? Quantum gravity. Again, my contention is we don't know if my friend Paul Steinhardt is right or if Sir Roger Penrose is right. There is no initial singularity. And even Stephen Hawking, had the no boundary proposals, etc. So and it's usually touted that we need a theory of quantum gravity because we know the universe had a singularity. Actually, we don't. And so I would like to know if there was any way to show that the universe had a singularity.
I think we need a theory of the early universe that's sufficiently concrete that you can calculate observable consequences of it. And we know what we have to calculate. Certainly some things that should be calculated that presently are not. Those include the amplitude of the fluctuations, the nature of the spectrum. Are they non-Gaussian? It would be nice to make some predictions for a change instead, right? Is there a significant gravitational wave background? What is it? What's its amplitude, and so forth? And there are many, many things that observers like you are gathering information about, and wouldn't it be nice if the theory predicted some of those things?
Yeah.
Or even post-dicted some of those things.
Retrodictions.
It's not that there's no material, it's that the theorists have failed to produce a theory so far. That's so. And so I want to. You can't blame the universe. You face it, guys. You failed. I failed.
Well, hope abounds, because Einstein provides a lovely target and a lovely kind of story. And I think, as you know, stories are very important to tell a good story, even in physics. But getting to this point, you make the case in the book, and of course we're talking with Frank Wilczek, winner of the co-recipient of the 2004 Nobel Prize in physics, along with Pulitzer and Gross. And this question, we talked a little bit about the Nobel Prize and what it felt to wait for 30 years, what it felt like on a personal level. But during that time, you were making tremendous contributions. And some of those contributions rely on things that may best be seen in the universe. I'm speaking about the CP problem. Yes. I'm speaking about axions. And these are probably the hottest topic. I did a plot recently of axions as a topic in Cosmos, and you got the hockey stick going. Al Gore, a fellow Nobel Prize winner, is going to do a video with him on an elevator with axion citations going up to the moon. But the point I'm trying to make is that that's another example of low energy limit of a potentially high energy phenomena. So do you want to say, of all these things that you've created, first of all, I can't resist, because how often do I get to chat with you? Of all these kinds of things, which would you most like to see confirmed, or if you're, I think, as you are intellectually honest, maybe disproven in the remaining 80 years of your life, hopefully?
Well, I think clearly axions are the biggest deal because they are, as you know, they're a leading, and perhaps, as you were hinting now, the leading candidate to provide the dark matter of the universe. They have all the right properties. And I've been cheerleading, but also participating in the attempt to design antennas, modified antennas suited to axions that will definitively observe that background, so it's not dark anymore, right? So we can see not only that it gravitates, but also does the other things that particles ought to do, although very feebly. So that's great. And by the way, you quoted Hertz recently. I feel very much that way about axions. It's a beautiful extension of the standard model. I think it's fair to say that the people who invented the theory, in some sense, Peche and Quinn, didn't realize its potential. They didn't realize it had axions, for heaven's sake, and much less that axions play such an important role in cosmology. But it's there. I mean, it comes right out of the equations when you think about them carefully, and then there's been a wonderful creative activity in trying to design the antennas, and we'll see if they're out there. It's just now in recent years getting to the point where the antennas are getting sufficiently sensitive that they have a chance to actually observe it. So it's very exciting, but nerve-wracking.
So before we turn, if you've got a few more minutes before we turn to a couple more questions from the audience, I wanted to just see if you'll indulge me. In your book, you talk a lot about religion. I joked at the very beginning, we spoke how your book in audio form, which I listened to in addition to reading it, I have the audiobook version of it, and it has 220 chapters in the audiobook versus the video, or versus the New Testament, which has 260 chapters. And you talk a lot about this character in the New Testament called Doubting Thomas. And I want to ask you, and maybe just to recap that, and maybe even your connection to I understand you're a Catholic, but not in good standing, perhaps, or not practicing Catholic. You call yourself a
very, very lapsed Catholic.
You call yourself an agnostic, and I wonder, what do you see similarities between sort of the faith that it takes to pursue a scientific idea that you believe is beautiful, ecumenical, or simple, economical, and to keep that sort of faith in the face of perhaps overwhelming odds? But is there anything about religion, or not in practicing theological sense, but are there any kind of fruitful interchanges that can be had from questions of faith as a physicist?
I'm not sure I would call it faith, but one thing that got deeply imprinted on me as a result of my religious training as a young adult, really, I turned away from it as in my early teenage years. So we're talking about very early, but very formative influences. And the thing I took away from it permanently, I think, and is really deeply embedded, is the idea that the world embodies secret meanings. That the surface appearance of things is not the real story. That there's something else going on that's in the case of religion is mostly symbolic, or sort of working out of a moral scheme. But in science, you take it as it comes. You go out and learn about what God is by studying His works. That's the attitude I have, and I don't think faith is, it's not a matter of faith, I would say. It's a matter of what I call radical conservatism, which is you have an idea, you work out its consequences as hard as you can, because you want to know if it's correct or not. And if it is correct, you've learned something very exciting. If it's not correct, you've also learned something useful that you should do. But vague thinking never gets you anywhere. So that's a kind of attitude that has something in common with religion, where you try to understand everything in terms of God, but I'd say it's a tenuous relationship. So it's not faith. I wouldn't call it faith. I'd call it kind of a working principle of pushing, but also of it's not a matter of appreciating. To me, when I was a very young adult, as I mentioned. Until I got disillusioned, I got enormous satisfaction about thinking that the world had deeper meanings, that there was a part of a big picture, that you could be a saint, and so and merge with God or something. But And of course, unfortunately, I can't believe in that stuff anymore. It just doesn't hold together as I've learned more about how the world actually works. But the way the world actually works is incredibly beautiful in its own way, incredibly beautiful. And I'm happy to be a part of it, and happy to be able to appreciate so much and learn more and more.
It's fitting for an author of a book about so-called beautiful questions that you'd answer that in that way. Okay, we're going to come to the end soon, but not before we take one more super chat. I can't resist the super chats. They put bread on the table. No, they don't do that, but they're very much appreciated. This one's from Jody Geiger. I wonder if he's related to the famous Geiger Marston, and the only man I think who's a physicist, Nobel Prize winner on a piece of legal tender. Do you know who that is, by the way, Frank? Nobel laureate who's on a piece of legal currency, not in America. Hint.
I don't know for sure. I thought maybe Rutherford was in New Zealand.
That's right.
Oh, okay.
Yes, Rutherford. Absolutely. Very good. That was trivia that you got. Anyway, going back to Geiger, maybe he's related to Jody. Let me know if you're related to Geiger Martin. Anyway, he asks, I have a peer-reviewed, published theory of everything with 20 plus measured and verified predictions in the laboratory, such as quantum gravity. But this work went unnoticed for years. So he's asking you for suggestions. How should he proceed? He says it's peer-reviewed and published. I don't know where. I don't know what experiments that verify quantum gravity he's talking about, but I get this a lot. How do we proceed with a novel theory of everything? What would you recommend to somebody, Frank?
I would recommend that you take a small part of the theory that people can understand independently, if that's possible, and if you have a clear prediction, write that up, and write it so that it follows from the minimal hypotheses, so that people don't have to work very hard to understand a complicated theory in order to understand anything at all. And then submit it to regular journals or post it on the archive where it can get the attention of people who are in a position to judge.
Great. And the last question from the audience that I'll take in the interest of time comes from someone named Zolo. Does Gödel's incompleteness theorem have any implications for physics? And I'll do another separate question in his second topic. But I always find that physicists have a sense of math envy, in that, at least in math, we know the limits of what can or can't be proven self-consistently, but no such thing exists in physics. And people usually say Karl Popper said falsification. Is there an analog to Gödel's incompleteness theorem, in your opinion, for physics?
Not really. Gödel's theorem has very much to do with, well, in a limited sense, which I'll come to. Gödel's theorem has very much to do with the properties of formal axiomatic systems. And physics is not that. Now, maybe there are long-term aspirations to turn physics into that, and we're nowhere close to doing it at present. But if we got there, then ideas around Gödel's theorem would become relevant.
Very good. Okay, so I'm going to now ask you my own questions that I ask all my guests on the Into the Impossible podcast. Hopefully you'll enjoy these. So normally when I have on, say, like a child psychologist, I say, now's time for the final 3 questions. First, can you provide a quantum theory of gravity that's self-consistent? And the child psychologist, give me 5 minutes. But now I'm going to ask you, because you've already worked on that. I want to ask you, there's a concept in my religion, which is Judaism, of what's called an ethical will. And it's what you want to leave to the future to benefit humanity. And actually, Alfred Nobel, who you're well acquainted with, had an ethical component in his material will, which was to make humanity for the betterment of all mankind. I want to ask you, what aspect or wisdom would you most want to leave for future generations as a so-called inheritance, an ethical will of wisdom, perhaps, for the future?
Well, I think that's what we'll discuss in our next podcast.
Okay.
because this is very much the kind of question that I take up in the new book.
Oh, awesome. I cannot wait. And we're talking about Frank's next book is coming out in January, on January 12th. He'll be on the show January 11th. Let me know if you want me to have him back live like this, or we could do a recorded one. But this is called Fundamentals, 10 Keys to Reality. I'm going to put a link to purchase the book in the show notes, so Frank you can get a head start in advance of our podcast on January 11th. Okay, let's get back to my other question that I ask people. Maybe this too will be covered in Fundamentals, but this is related to the namesake of this show, is Sir Arthur C. Clarke. And I am the co-director of the Arthur C. Clarke Center for Human Imagination. I think I've mentioned that to you once or twice. I've invited you to come when the pandemic is over. You'll come and we'll do an event around you and your wonderful books. But there's a scene in the movie 2001, A Space Odyssey, based on Arthur's books and a series of books. And it shows these primates on the plains of Africa, and they're playing around with this monolith that they discover. Right. And then later they discover it on the surface of the moon. And yesterday I talked to astronaut Jessica Meir about this, about her experiences. And she said she gets like PTSD thinking about the HAL spacecraft when she was on the ISS. But anyway, I want to ask you, Frank, the monolith in 2001 is like a time capsule. What would you put on a time capsule if you knew it would last for perhaps millions of years into the future? What summary of nature would you perhaps put in there?
Well, we have the equations of the Standard Model that are perfect for that purpose, because they can be stated very precisely and concisely in a computer program. So we could certainly write such a program, and it would be much shorter than the operating system of your computer, certainly much shorter than Word. And I put in axions as a plausible extension of the Standard Model, and I put in my new book.
Which form would you put it on? CD-ROM?
But what's gonna last? Well, it's very. I mean, technology and science have changed so much in the last 100 years. It's really nuts, in my opinion, to think about what would be interesting to the humans or cyborgs or inheritors of human intelligence that would be looking at these things even thousands of years into the future. So I guess I'll leave it at that.
Okay.
That's the best answer.
Yeah, I'm just afraid I'll put it on a USB stick, and we only have USB-C. We don't have USB-A. Okay. Lastly,
of course, I would also, I should say, I don't want to belittle the achievements of observational astronomers. Of course, independent of how the world works, we also have a lot of information about what the world is and was, and we'd want to have a nice summary of that as well.
That's right. Yes, and that will hopefully be contained in our next podcast. We do that in a couple of weeks. The last question I have for Frank is also kind of related to Sir Arthur C. Clarke, who said, as you quote in the book, I'm talking about your previous book, A Beautiful Question, which I devoured over the last 187 hours of listening to it on audio. But the quote comes from Sir Arthur C. Clarke. One of them is relates to his 3 laws. And his first law is that for any sufficiently advanced technology is indistinguishable from magic. You quote that in your book. The second law, which is a little bit less well known, is for every expert, there's an equal and opposite expert. I find that to be true. And then the third law is where we get the name of this podcast. He said, the only way of determining the limits of the possible is to venture a little way past them into the impossible. And that's the name of this podcast. I want to ask you, what mysterious aspect of life perplexed you as a 20-year-old or a 30-year-old when you were coming up with these soon-to-be, or not soon-to-be, but future Nobel-worthy things perhaps, was perplexing, mysterious, maybe fear-inducing, but now makes sense through the lens of looking backwards in time. So essentially, advice to your former self. What would you tell a 20-year-old Frank Wilczek?
I tell them to focus more on the basic aspects of quantum theory. Early in my career, I had a kind of snobbish attitude about people who worried about the foundations of quantum mechanics. I said, I mean, come on, we use the theory all the time very successfully, and there's not the interesting thing is to apply it in complicated circumstances, not to understand the basics. But in recent years, it's really become clear that the theory is so deep and has so much potential that's been untapped for information processing and new kinds of sensitive detectors and new ways of understanding the world, that it would have been better to get earlier into the issues of understanding really very, very basic questions and not to turn up my nose at it and sort of brush it off.
Very good. We have one more guest question that's going to come in from actually live by Skype. We'll see if we can get him on. This is Eric Weinstein, who's a friend of the show, who runs his own podcast called The Portal Podcast. Let's see if Eric can be patched in somehow. Eric, do you hear us?
I see his name.
Yeah, I see his name, but I don't see him. Let's see if he is available. I will check to see. There's technical difficulties. Let's see if this will come up. This is always challenging. Oh, I think he might be popping in.
I'll leave it at that. Okay.
There he is. Let's see. I hear Eric. Eric, how do you read us?
I can see you.
Okay, we cannot see you.
I can hear you now, but not see you.
Hey, Frank, it's been years. Good to see you.
It's very nice to not see you, but to hear you anyway.
So, this is a great thrill, and there are issues that I've wanted to talk to you about for some time, particularly with...
Sorry, Eric, you dropped out.
You left an extremely provocative comment in the book, which you pardon me?
It's a little hard to hear you. You're breaking up a little bit, Eric. What was
it? Breaks up a bit.
What's your question?
Maybe
there we go.
Oh, there we go. Now I see you at least. Then.
Okay.
Very good.
So, can you hear me now?
Yes.
Yes.
So I wanted to ask you about a question from your last book, which you tantalizingly drop in a provocative fashion and then deliberately don't follow up, which I thought was a great literary move. Which is that you talk about the SO10 theory of grand unification, so 3 out of 4 forces. And then you say, I note that this is the same representation of spin 10, that is the spinor representation, as the portion that connects to the space-time, which is the space-time spinor representation.
Yes.
And then you say, whether this is a coincidence or an indication of something deeper is not known, or something like this, and then you run away.
Well, in my private notebooks, I've tried to follow up on that, and not only in my private notebooks. I mean, I've thought about models where you extend the spinor symmetry to explain why there are families, but that doesn't bring in space-time, but there are also attempts to bring space-time spinors and internal space spinors together. I never published any of that because it didn't work to my satisfaction. But it's still an interesting program, and maybe somebody would have better ideas about it. I mean, it's a remarkable mathematical coincidence that these same structures emerge in such different contexts. Yeah. And I don't know, I have this sneaking suspicion that it's like the equivalence principle. It's something that everybody knows that points to something very deep, but I haven't been able to get that deep and get it out.
Well, you should know that I spend my every waking moment trying to make that cryptic comment go down in history as one of the most important. But you also probably know that the number 10 doesn't get a lot of attention when you talk about the SO10 grand unified model, because what that group of symmetries of 10-dimensional space is doing for the model is not happening in the 10-dimensional incarnation of the group. It's happening in this 16-dimensional Weil spinner representation.
The representation, right.
And so my question to you would be, what concern have you given to the 10 in spin, or SO10 as the physicists call it, which is really spin?
The SO10, the group, as you know, governs the not the quarks and the leptons, but the gluons and the weak bosons and the photons. So the force mediating particles. And there are new ones that arise in the bigger theory in the SO10 that mediate things like proton decay and generate masses for neutrinos. And so I've very much followed
but that evades the question again, sir, because that is the 45-dimensional representation of spin 10. We have 16, and we have the 45. I'm still trying to get you to answer the question about the 10.
Well, the only place. Okay, I mean, well, I don't. You
have to appreciate that because I'm a non-physicist, I get to ask these things. Whereas if I was a professional physicist, I'd have to worry about their consequence.
Yeah. Well, it's an artificial separation because to me the dimension of the space, so that there's a 10-dimensional representation, there's a 45-dimensional representation, there's a 16-dimensional representation that all play important roles in the theory. The 10-dimensional representation actually does play a role in the theory. That's where the Higgs particle lives.
Well, so this is an interesting question.
The fact that you call SO10 S10 is really just a label. You could call it G for group. It would still be the same group, and it could be represented in different ways, some of which are 10-dimensional, some of which are 45-dimensional, some of which are 16-dimensional. The underlying symmetry
that's actually not really the case, because spin 10 and spin 9 are a very important transitional period where the first, let's say, 1 through 9 dimensions gets you through what would be called the exceptional isomorphisms in Bott periodicity. But above that level, the group has different properties because it stops acting transitively on the orbits of its spin representation. But let me ask you another couple of questions. You're aware that you had a 14-dimensional. What?
I think we're going to lose the audience very, very rapidly at this level.
Brian?
I'll allow one more question, and then I do want to remind people that the number 10 is very important because Frank's next book is Fundamentals, 10 Keys to Reality, not Spin 10. I promise Frank would be off at the hour. Eric, we'll take one more question from the audience from you. Let's make it a little brisk.
Okay. All right. So the one question I also would have asked is, I have a feeling that you think that it might be that some of the spinless fields that we use, whether the inflaton, whether we're talking about quintessence, whether we're talking about the Higgs field, might be related to each other in a way that has not been fully understood. Is it possible that any of these fields that we invoke to sort of get out of jail for various problems elsewhere could be the same, like you never see Clark Kent and Superman in the same place? We think that these are distinct fields, but maybe they're different. Maybe they're the same.
They certainly could be the same. And people have explored, I'd say with mixed success at best, the idea that the Higgs particle and the Higgs field and the inflaton are the same thing. I think more likely is that we'll find a more encompassing theory that has all these different particles as consequences, so that we'll see that they're not really independent ideas, but they'll be unified at the level of concepts, not at the level of identity.
Very good. Thank you, guys. Thank you especially to my guest today, Frank Wilczek, who is the author of this book, A Beautiful Question, which is a beautiful book, Inside and Out, beautifully bound, actually, and lavishly illustrated with colorful representations of different objects, including some spin groups that we just heard about. But I want to also notify people that we are going to be live with Frank Wilczek in a month to talk about his new book, upcoming book, Fundamentals, 10 Keys to Reality. Frank, I want to thank you so much for going into the impossible. I want to ask the audience to tune in and subscribe to hear interviews with Barry Barish, Ray Weiss, fellow laureates of Frank Wilczek. And also, hopefully, we're going to get C.N. Yang, Frank Yang, another Frank Nobel laureate. And I'll bring on Frank. Frank, I hope I can bring you on if I do manage to pull that off, you and maybe Shelley Glashow and also Jim Simons. But I'll keep you posted. Frank, get back to...
That would be extraordinary. I promise not to be the fly in the ointment. If that comes to be, I'll move heaven and earth to participate.
I will do my best. Thank you so much. We loved having you on. Everybody out there, thank you for going into the impossible with Brian Keating. I'm your fearful host. Looking forward to our next episode together. And now, intro, outro music from my friend Miguel, Yeti Tears Online. Thank you, Frank. Thanks, Eric. I'll see you hopefully maybe later tonight.
I'm going to sign off now. So bye-bye.
Bye, guys. Eric, how are you, my friend?
Look at you, Mr. Big Shot Podcast.
I know.
Talking to all the smart people.
Well, you missed the beginning. I asked him about imposter syndrome when it came to the Nobel Prize. As I asked Barry Barish last week when he was on the show, that interview will come out soon. I asked Barry, did you ever have imposter syndrome? And he said all the time, especially when he went to go collect this little medallion and he sat to sign the same book that this guy's name was signed in just above. And he said, I never felt more of an imposter in my whole life. I asked Frank Wilczek, what do you think he said?
About imposter syndrome?
Imposter syndrome.
Not since breakfast.
No, not since he was 12 years old. He took an IQ test as a high schooler in Queens, New York, and it came out phenomenally for him. And it's been all the way for him. But he did say that he wished he had maybe spent a little bit more time learning quantum field theory, which I found kind of a kick in the tail. Because if he's got problems with quantum field theory, what hope do I have?
Well, I think that that's a really interesting answer because in large measure, quantum field theory is the only thing that really underwent a major intellectual revolution after Frank. So Frank is the last person, literally the last person to contribute to the Standard Model. He's now 69 in terms of youth.
Yes.
The thing that happened after him was the geometrization of quantum field theory. And in some weird way, if you preceded a paper called Iguchi, Gilkey, and Hansen, you think about the world one way, and if you followed that paper, you think about it a different way, because that was the paper that introduced geometric language to the physicists. Mm-hmm. And then, so many of like Witten's insights. Frank belongs to an earlier world. Ed is born later the same year, and he's on the other side of that divide. So Wilczek to Witten is the divide, in my opinion, as to where we become smarter and dumber at the same time.
But I also mentioned the quote from T.S. Eliot where he said, no one's ever done anything after he won the Nobel Prize. It's like a ticket to their funeral. And it couldn't be farther from the truth in the case of Frank Wilczek, who was 22 years old when he came up with asymptotic freedom with David Politzer and David Gross, had to endure.
He didn't win the prize for a long time.
34 years. I mean, can you imagine that? Or 31 years. I couldn't imagine. I said, how was that feeling? And it basically sounded like he was excruciating. By the way, I think we're inventing a new genre right now, Eric. Podcast debriefing in the middle of an active live podcast stream on YouTube. But I love it. I'm here to break barriers and go into the impossible.
Well, there you go. I mean, I also thought that his responses, this throwaway comment that he made about spin 10 and the regular spinners on space-time, we hit pay dirt because what you're hearing about is that this is a private research program and that people are embarrassed to air their sort of private thoughts. This was a daring thing to do in the culture, but it shouldn't be daring at all. I mean, how important That idea, I believe, is going to turn out to be one of the most important ideas ever.
Yeah. So I want people to tune in tomorrow. Hopefully in person, we'll have Eric Weinstein with better audio quality, not better video quality. You've got remarkable video, and the audio just needs a little bit of tweaking. But I bought you a present. I got you a present here. Well, it's over there. It's a microphone, Eric. I hate to spoil the Hanukkah surprise, but I got you a microphone. A real live microphone.
Last year was Preplock.
There's only two things that people say about you when you come on my show: how handsome you look, how much weight you've lost, maybe three things, how you need a better microphone. So we're going to do that. And maybe something about publication, but we're not going to go there. That's a sore spot. We're going to talk about that in person tomorrow.
What did you think of your interaction
with Frank?
Yeah.
Oh, yeah. I thought it was marvelous. He actually echoed some things that I've been thinking about for a long time, and that, I'm going to run by you in person tomorrow. And that has to do with, why don't people test the low energy consequences of their models using existing data sets? So imagine if I said to you, I've got this great theory, but it requires an atom smasher that's twice as big as LHC. Well, I could say to you, well, I've got this thing. It collides two 30 mass solar mass neutron stars at 99.9997% the speed of light. Would that interest you? Does that have any relevance to your theory? And he basically said, yeah, those are the kinds of tests that you want to look at for consequences, low energy. And he gave the example that he published with Lawrence Krauss, called From B Modes to Quantum Gravity. This won some prize in gravity research in 2014 after Bicep 2. But before it was retracted. And that was anticipating whether or not you could actually say that gravity is quantized from low energy phenomena, such as B mode polarization, the kind of which I studied. One thing I thought was really cool is looking at his book is a lot about color and light, and he goes through these beautiful examples of beautiful things in nature. There's a beautiful squid. We'll be having that for lunch when you come tomorrow. But the beautiful things in nature that Isaac Newton discovered. You remember, he unified spectral theory. Color theory was not thought to be part of physics. It was like mysticism. Maybe it happens in the eye. Maybe it happened. But he showed you have a prism, and you take a spectrum of the sun, and then you block out the color green, let's just say, and then you put it together with another prism. So you do a summing operation, and out doesn't come white light. And that was a demonstration that it's not a physiological property. So he unified within the laws of physics, so to speak, empirical evidence at low energies, which we'd later discover, as Frank talks about in the book, at high energies has a consequence in Maxwell's theories, which he basically views Maxwell as his superhero, as his avatar in physics. And I can't fault him for that. But I kind of view Faraday myself, because Faraday would do the experiments without any mathematical knowledge. And I think the experiment is the key. I've told people in the chat room right now, leave a thumbs up if you have heard a theory of everything lately, and then leave a comment in the comment section if you have a theory of everything, because it's
rough comment section, man.
That's right. I know it's going to be brutal. That's a high bar, right? All right. Well, I'll let you go. Thanks for coming on. Tomorrow, let's do a live stream. I want to talk about this new idea, a project that I have to act as a Weinstein-Keating sieve to get to the root of what it means to have a working theory of everything. Until then.
Well, such an exciting invitation. I'll even come down to San Diego. What do you think?
All right. I've got room on the couch here. We'll both be in the doghouse when my wife figures out how much time I've been spending podcasting. Everybody out there, I love you guys.
On our couch.
Please.
Crisscross thing. It's like strangers on a train. We'll both sleep on each other's couch.
Everybody, thank you so much. Please subscribe to the podcast so we can get more great guests like Eric and Frank Wilczek. And next week, we're going to have Kamran Vafa. We're going to have Barry Barish. We're going to have Carlo Rovelli has agreed to come on. And Oprah. And Oprah is coming on to give me a new couch. Everybody will get a couch.
Everybody gets.
So for now, signing off, your fearful host, Brian Keating. Have a great day, everybody.
Thanks.
Bye, guys.